We continue with HP1 now, and we have two examples. So this floor is yours. And here we have
Today I'd like to show one of the HP1 application to the nitrogen transport. When the organic matter is applied to the soil, the degradation of the organic matter called mineralization produces ammonium. The nitrification from the ammonium produces nitrate, and denitrification produces nitrogen gas. But when high CN ratio organic matter applied, the ammonium deficiency occurs for the production of the humus and the biomass. In this case, the immobilization, the deficiency of the ammonium compensates from the ammonium in the nitrogen in the soil. This is called immobilization. Then, when the deficiency occurs, this also slows down the organic matter degradation. Then, in order to describe this process, it is necessary to couple nitrogen cycle and carbon cycle. There are several existing programs to describe this nitrogen carbon model. The original is the most of idea come from Johnson. As probably you know, Chen is also used the idea from the Johnson. This is the basic structure of the nitrogen and carbon model used in the Chen. Upper part is a carbon cycle model consisting of the two organic pool, and the lower part is nitrogen cycle and transform model. As you know, the HP1, the Hydrus take care of the non-reactive solid transport, and the Brixie describe the reaction. Of course, then if we can describe the nitrogen carbon cycle model here, it is very convenient because obviously flow and transport is very accurate and reliable in the Hydrus. Then, today the time is limited. I'd like to briefly describe the nitrogen carbon model. Then, at the end, I would like to show some HP1 example with some transient water flow conditions. Degradation of the organic carbon result in the three components. One is biomass carbon, humus carbon, and calcium. Carbon dioxide. We assume the ratio of each component is constant. Then describing using two factors defined like this efficiency factor and humidification factor. The ratio of humus might be different depending on the organic matter, but the ratio of the carbon dioxide will be around 50%. The basic idea, basically, the degradation of organic carbon is described with first-order kinetics, this equation. The basic strategy for the model formulations, we try to relate all the other relations with this equation. Since we define the ratio of each component, we can describe the production of each component using this organic carbon degradation rate. Then, considering the mass consideration, we can describe the net organic carbon rate as a sum of the decay and biomass recycle. I'm sorry, we assume the biomass is recycled in the pool. Then carbon dioxide rate is also production from organic pool plus the production from humus, like this way. Then we also define the organic nitrogen degradation, like this way. Also, we define the CN ratio for each component. The CN ratio for the biomass and humus is generally around 8 to 10. It's generally constant. Then we can relate the degradation of organic nitrogen with the degradation of organic carbon using the CN ratio. Then we also use the fast kinetic for the organic nitrogen degradation, but we can relate with the CN ratio like this way. Same as true for the biomass nitrogen production and humus nitrogen production like this way. Then if the supply from the organic nitrogen exceeds from the demand for the production of the biomass and humus, in this case, the mineralization occurs. If the deficiency occurs, immobilization occurs, like this way. Then the CN ratio for biomass and humus are the same. The equation can be simplified like this way. This equation is very important. Then, for example, the CN ratio is 10 and the efficiency factor is 50%. If the CN ratio exceeds 20, immobilization occurs. But I mean the nitrogen deficiency occurs. On the other hand, if the CN ratio below 20, mineralization occurs. In case of the immobilization, the amount of ammonium can slow down the degradation. We define the maximum available ammonium per day. In the leaching, we assume 10% of the concentration, like this way. Then we define maximum degradation per day based on the available ammonium. Using this, we define three stages. One stage is if we have a stage one is the amount of ammonium is enough. The second stage is the ammonium deficiency start. In this case, we use maximum degradation rate. Then third stage, almost no available ammonium exists. In this case, we stop the biomass and the humus production. Then only carbon dioxide ammonium produced with very small rate coefficient. This stage is sometimes called nitrogen starvation. Then, similar to the carbon, using the mass balance consideration, we can define the net organic nitrate degradation rate, humus nitrogen rate, as a function of the organic carbon concentration. Then we can also include the transformation with ammonium nitrate like this way. Then we also can have a net concentration, the rate coefficient, but we add here mineralization or immobilization factor here. Then, like Didrik mentioned, everything can be included in the fluid C based on the first order kinetics. See, Then, once we succeed to describe this reaction in the Flixi, it's very straightforward to implement in the HP1. Then, we can calculate the various flow and the various anisothermal conditions. Then, let me show the two examples of the under the infiltration into silt with anisothermal condition. Here, I just only think about one organic pool, but CN ratio is low, 5 and 20, high is 30 and 100. Then, in this case, we just neglect the initial ammonium and non-nitrification, just for the sake of simplicity. This is a result of the organic concentration profile for CN5 and CN20. Because nitrogen does not affect the degradation, results are same. The organic carbon concentration decrease with time. At 40 days, this disappears. All the organic matter disappear. Same as true for the organic nitrogen, but for the lower CN ratio, of course, has higher concentration. Then, this reduction goes to the humus and the liquid phase of the ammonia. See, then because of the high amount of the ammonium, the nitrate, the ammonium concentration is greater for the CN5 than for CN20. This is a case for the high CN ratio, which immobilization occurs. This is for the CN30 and CN100. This is organic carbon concentration. The situation is more complicated because nitrogen concentration can control the degradation rate. See? Here, like this way. And also, it goes to this. This is organic nitrate concentration profile. In this case, for example, here, the stage 1, stage 3 occur near the surface, but the stage 2 continue the lower layer. But in case of CN100, stage 3 keep on going until 100 days or so. This is a CN ratio profile. See, as mentioned, below the CN20, the immobilization occur. Mineralization occur, which means at 40 days, mineralization started near the surface, but immobilization still keep on going here. In case of the CN100, the stage 3 degradation occur very slowly. At the final 100 days, the stage 2 slow degradation start occur only the lower part. Then this is ammonium concentration profile. See, as can be seen, it's very complicated. But here, because of the mineralization, at 40 days, the ammonium concentration increase. But here, still immobilization. Then ammonium concentration is very low. These are the demonstration which I did. Then I have already implemented almost all the reaction in the lithium. These are the possible modification which I'm going to do. The multiple organic matter. I have already included the 2 organic matter. Like he said, I don't know how many organic matter pool we should have, but probably 3. From a modeling point of view, it would be better to have a 3, but it's very straightforward to include several organic pools. And also, good solid active. Didrik mentioned he has already solved this problem. I can put some statement in the Flixi, then we can have a different active, root active for ammonium and nitrate, the CO2 diffusion. This was also he mentioned, then I can include. Then I would like to include the cation and anion exchange for ammonium and nitrate. This needs a little bit more consideration to satisfy the mass balance and the charge balance, but Dietrich might have some idea you can solve probably. Then I would like to include pH dependency, CAC, then immobilization of the nitrate. This would, and maybe oxidation reduction reaction would be possible. That's a little more curious, please. Thank you.
We have time for one question to give Dietrich a little bit more break. If there is any? Does not look like, then thanks again. And then it's time for Dietrich again.